Thank you very much. So it's a great honor and a great pleasure to be able to speak at the conference for Hélène. I remember a long time ago, I don't know if you remember this, Hélène. I remember a long time ago I got a little card from Germany when I was just the first beginning postdoc, I think. You know, at the time we used to send, people would send cards asking for a copy of your preprint. And I said, a card from Germany asking for a copy of my preprint? Well, what's going on here? So that was really nice. Very nice to have somebody interested. So in fact, I think all along all of the stuff I've been doing about local systems and stuff like that, it's really nice to know that Hélène is such an enthusiastic fan of everything about local systems. And I think what we'll see today here reflects that in several ways, notably the idea of the Gauss-Bonnian connection and the idea of Chern classes for bundles and parabolic structures and stuff like that. Okay, so let me start by the general setup. So let's just fix as a general setup. Let's fix a Hitchin moduli space. Of, let's say, some kind of Higgs bundles. On a, let's fix a curve C. And then so so we have a basic picture which is sorry. This should be. Okay, we have this basic picture. So the F is the Hitchin map. B is the Hitchin base. Which is basically, it's the set of C tilde containing T star of C, which are spectral curves. Of whatever Higgs fields show up here. And pi, so now x, what's x? So x is going to be So X is going to be basically a coarse moduli space of bundles, but this, in some cases, this could be something different, which I'll talk about in a minute. And so pi is the map, which takes E comma phi to just E. The isomorphism class of E. And this is not everywhere defined. Okay, so because in order to get a coarse moduli space, we want to say semi-stable bundles or something like that. So not it's not defined if E is not itself a semi-stable bundle. In the other direction, if E is a semi-stable bundle, then any Higgs field on E will also be a semi-stable Higgs field. But you can have, in fact, almost always have Higgs bundles whose associated bundle is not semi-stable. Okay. And at those points, the map pi is not defined. So pi is only a rational map. Okay. Now we can give a sort of an intrinsic description here. Which is we have a C star action on the moduli space of Higgs bundles, and pi of y is the limit as t approaches 0 of t times y. Okay, and this allows us to extend the situation to cases where X is not necessarily a moduli space of bundles. So, so in general, X could be well. Let me explain this. Let me first define the subspaces here. So we have fixed containing nilpotent. So the nilpotent cone is F inverse of 0, and this is the fixed points of C star. Now, of course, I mean, this is an algebraic operation, so the limit of the action on the point is going to be a fixed point. This exists. The limit exists because F is proper. F is proper, and the C star action sort of contracts things in the Hitchin base.
May I have a question?
Yes.
Are we over complex numbers?
Yes, we're over complex numbers. Yeah. Thank you. I have no expertise at all over anything p-adic or characteristic P or anything, although maybe I'll try to make a comment later. But sorry, I'm sorry. Let me apologize. Yeah. Okay, so right. So now, what is X? So X is just X. X is the component of the fixed point set. I mean, let's assume we've taken a connected component, so this is going to be connected, irreducible. So X is the component such that limit T of Y is in X for if Y is general. Okay. So anytime you have a situation like this, let's say a proper map to a vector space and a birational map like that, this defined with a C star action. With a C star action that covers the C star action here, then there will be one of the components, and there's going to be one of the components of the fixed point set, which is the limits of almost all the points of MH. Okay. Now, some points, of course, can go to limits that have, that are in other parts of the fixed point set, but that's going to there will be a proper subvariety of MH where the points have some other limit. Okay. So that uniquely defines X, and we can use that to sort of extend the situation to cases where X might not be a bundle. So if C has a divisor and we look at parabolic structures, then we can have the same setup, except that where X is not necessarily a moduli space of bundles. And X is going to be a moduli space of parabolic Hodge bundles with some non-trivial Hodge decomposition. Okay, so I wanted to say that because, well, most of what I'm going to say today is just in the case where X is the space of bundles. But to insist upon the fact that this general setup looks very general and should apply to cases like this also. So let me just comment that there was work of Toulis Tolosan a few years ago that said that such X can be compact components of real character varieties. and recently work of Lam Landesman. Give some discussion of the situation. I'm not sure if I'm stating this correctly. You guys can correct me here. But in some cases, let's say in some cases these are related back to the bundle case. By Katz's middle convolution. So, you know, it may be, it's possible that maybe you only need to look at the bundle case, but a priori there seem to be some new cases like this. Okay. Okay, so anyway, so that's the general setup. Now, what are we going to do within this setup? So the main point is let's define the wobbly locus.
So tell us, like general setup, you mean you just have some moduli space and there's a C star action and then everything's good? Or?
Well, let's make it be a quote Hitchin moduli space for whatever that's worth. I mean, I'm going to talk about this in just a very specific case where.
I just wanted it. It's interesting to have a general setup.
Yeah, well, so you know, so there was a paper. There was a paper by Paul, I think, saying that in some general situation of intersections of quadrics or something like that, you might have a similar setup like that. You know, it's not wouldn't be unreasonable to conjecture that any kind of setup that has all the formal properties like this probably comes from some kind of Hitchin system in some way. Maybe wild or something like that, but anyway.
So do you want to replace X by fix here and have an actual map pi or not?
No. I mean, okay, you might be able to do that too, but that's not what we're doing. X is the bottom component of fix.
Right, so you don't want to have an actual map pi.
No, we're not going to have an actual map file. We're going to work on that later. Yeah, maybe, let me just explain the terminology bottom component here is because the Hitchin defines an energy function on the moduli space, and the critical points of the energy function are also the fixed points of the C star action, and this X thing is the lowest energy fixed point. Okay, so we think of it as the bottom in some case. And you think
Sorry, just a question. So by modular space, you consider what's structural?
Well, as a variety usually or a scheme. I mean.
But when you talk about C star action, it's like algebraic.
Algebraic, yeah, algebraic. Everything is algebraic geometry over C unless otherwise stated. Okay, so what's the wobbly locus? Let's just define it to be. Take the nilpotent cone minus X, so everything in the nilpotent cone except for X, then close that up and then intersect that with X. And this is a divisor in X. So there's some people have given that, given a theorem to that effect. I think it's basically a consequence of the fact that nilpotent cone is a Gorenstein variety because I didn't write this down, but in the case, let's say in the case where MH is smooth and so on at least.
So you put X in MH via the unitary section, or you said you put in minus X?
Yes.
You didn't explain, or you just...
Yeah, I'm sorry. Yeah. So X is a subspace of the, X is one of the components of the fixed point set. So it's sitting inside MH. So we view it, but that's a good point. So in this general setup where X is bundles and MH is Higgs bundles, that doesn't tell us necessarily that bundles are sitting inside Higgs bundles. But yeah, this is really. Thank you. Right, the nilpotent cone is a complete intersection, right? Because it's the inverse image of 0, and B is a vector space. The Hitchin base is a vector space, so the image, 0 is cut out by a dimension of B equations, and those give you equations that cut out the nilpotent cone. And I don't think you can have a complete intersection that has two, where the singular locus sort of has codimension 2, But it has to be said that, okay, the nilpotent, this as a scheme, this is non-reduced. Okay, so this is maybe not a proof, but anyway. But people have proven this also. Okay, so in pretty much generality, let's say that the wobbly locus is a divisor in X. And now what happens? X minus the wobbly is X very stable. So this was defined by Lemont. So X is very stable if it doesn't have a non-zero nilpotent Higgs field, and therefore X is wobbly. Wobbly, that's the terminology introduced by Donagi and Pantev. Sorry, I should have said at the start, obviously, this is joint work with Ron Donagi and Tony Pantev, the whole thing. So it's wobbly. This is Donagi and Pantev introduced the terminology. If it's not very stable, it's wobbly, okay? But that's kind of stuck around. So anyway, wobbly if there exists. If there exists an nilpotent Higgs field. Okay. And now it's known, it's known or at least conjecturally known. So non-zero nilpotent Higgs field. Yeah. See, everything in X has a zero Higgs field. And the ones that have a nilpotent Higgs field but that's not zero, those are, if you go out in that direction, then that stays inside the nilpotent cone, and it's going to go and hit a upper fixed point set in the nilpotent cone. Let me just maybe draw that. Let me draw that over here, maybe. All right, see, if you're at the wobbly, if you're at a wobbly point, and you follow a non-zero nilpotent Higgs field sort of in the upper direction, then you're going to hit another point of the fixed point set. And these are the points that Phil was asking whether I wanted to include them. These are points that are in the fixed point set, but not inside X. Okay, this is X. Okay. And the wobbly locus is just everywhere where the nilpotent cone hits X. Okay. How do you, where's the thing to push this all the way up? Ah, okay. Okay, so now the geometric Langlands conjecture, I guess. Well, it predicts something complicated, but let's ignore the, the sort of ultra simple version. Predicts the existence of local systems on X minus wobbly. Okay, so for one thing, it's really it's usually explained in terms of stacks rather than moduli spaces, but X is a coarse moduli space of semi-stable things, so it's not really an open subset of the stack, but the stable points of X are open subset of the stack. And very stable implies stable. So this guy is going to be an open subset of the moduli stack, okay? And so the geometric Langlands conjecture predicts more generally kind of d-modules on the moduli stack Bun. But in particular, those are the ones that are supposed to correspond to the Hecke Eigensheaves inside there. Those are supposed to be local systems on the complement of the wobbly locus. Okay. So okay, so there's a kind of let me just explain. There's kind of interesting history here. In the Monin volume of Duke Math Journal. There was Le Monde's paper that said that, basically. And gave the rank, in the rank 2 case. So now I forgot the number. It's 3G minus 3, right? In the same journal, there was Hitchin's paper. Not his self-duality paper, but his paper on Higgs bundles, on compactifying. T star X. So where you get the Hitchin map, so you get, and if we take F inverse of B, and then we sort of rationally map it down to X, this has degree 2 to the degree. Okay, so I think I could actually stop the talk at this point. I mean, really. I mean, it's obvious if you look at these numbers, it's obvious what's going on, right?
Are you sure that he compactifies T star X there? That he just looks at the cotangent bundle of Bun G, the coarse moduli Bun G?
Well, maybe T star X stable.
Now, I don't think he partially compactifies. That's in the other paper just for SL2. If I understand correctly.
No, but I think in the Duke paper it's for SLN or something like that. I mean, he was discussing Higgs bundles of arbitrary rank, I think, in the Duke paper.
Sure, it's an arbitrary group, but I don't think he partially compactifies. That's in the other paper, I think.
Well, anyway.
We can have a look for it.
I'm kind of fudging the history maybe a teeny bit here. I'm not sure if he said in that paper that the degree was this, but Ron Donagi said, okay, when I was wondering about that when I saw this, pretty much right away was wondering about that. And so let me just give another part of why we think this, why this is why this is interesting, or why this is suggestive, is because so in terms of stacks, so on the level of stacks, this is sort of what Phil's saying. The moduli stack of Higgs bundles is really equal to the T star of the moduli stack of bundles. Okay. So on the level of moduli spaces, so MH is birational, let's say. To T star X. Okay. And so here we have a source of, right, so this F inverse of B it's a source of subvarieties. Let's put in quotes here, this T star X for now, whose degree is the rank, whose degree is the rank of the geometric Langlands local system. Okay. And so this suggests, it sort of strongly suggests that these might be the spectral varieties of the Higgs bundles, let's say of the Higgs sheaves. For geometric Langlands, I'll use a small g and a big L. Okay. And so that's what we'll call the Donagi-Pantev conjecture. So
in the conjecture, is there not like the input data of a local system on the curve that you want to sort of put in as a...
Yeah, I need to get to that. When we say the geometric Langlands conjecture predicts the existence, that this prediction depends on an input data, as you say. I'll say that in a minute. Yeah, maybe I should say that. Yeah, sorry. I guess I should say that right now.
Under the disk.
Yeah, thanks, Phil. Keeping me awake here. Right. So before stating the conjecture more precisely, let's discuss the data. Okay. So the input data for the geometric Langlands construction is we should have a local system for the Langlands dual group here, where G if G is the group is the structure group that we're using to talk about bundles and so on, then we should have an LG local system on C. Okay. And then we expect to get, so let's say perverse sheaf maybe. Well, I'm not sure I'll have too much time to get into this, but there's something called the Hecke correspondence. Which very roughly looks like that. Okay, so, and if we take R Q lower star of P upper star of F, so our F here should correspond by the correspondence to F box times lambda. This is very rough here, but okay. So that's the conjectured relationship between the input data, which is a local system, a Langlands dual group local system on the curve, and the output data, which is the local system on Bun, which is supposed to be a local system on the very stable locus. So I'd like to just insist here for this talk on the fact that we're basically trying to construct some local systems on this quasi-projective ride. Okay, now, so the Donagi-Pantev conjecture says that the so let F correspond to a parabolic logarithmic Higgs sheaf. This, again, is not really all that precise for reasons we'll discuss in a minute, but let's call this E. On the variety X relative to the divisor wobbly. Then the spectral data of E phi is the spectral covering with a line bundle L on a Y determined by the original lambda. Here again, I need to explain a little bit more, but let's just say determined by lambda via electromagnetic duality. And the sort of that, you might say this is maybe the basic version, and then sort of the more advanced question is to describe the parabolic structure. Okay, so now let's work on erasing stuff here.
Carlos, what's the subscript on the T star X? What's that?
Log.
Log.
It's the logarithmic cotangent bundle of X relative to the wobbly divisor. Which, as if you're thinking about this, you'll say, wait a minute, is that really well defined? Because what happens if the wobbly divisor has some bad singularities, which is indeed the problem. But
that's what I was going to say.
Yeah. Okay. Good. I thought you were gonna. I thought you were gonna say that, so I was gonna answer the question before it showed up. But anyway, yeah, that's exactly the problem. We'll hopefully get to discuss a little bit about that in a minute. But anyway, that this does have a good meaning along the in the x codimension 1 part of wobbly locus, namely the smooth locus of the wobbly locus. And also, I mean, it's limited in the sense that we really only need to go down to the x codimension 2 part, but that's the problem. Maybe I should say, when I say correspond here, this is by Mochizuki's theory. Takuro Mochizuki's theory corresponds very generally, even wild situations and stuff like that, but especially perverse sheaves are going to correspond to parabolic logarithmic Higgs sheaves.
So I think F is polystable?
Sorry?
Is F polystable then?
Yeah, that's going to turn out to be true, actually, as we'll see. Sorry, maybe let me go back a minute. Let's say for general points. Let's say if lambda is general. I'm not sure whether maybe you can ask them about it, but I'm not sure if they have a well-formulated statement for arbitrary values of lambda here. This is for general points lambda. And for general points lambda, the point in the Hitchin base is a general point, and so the Hitchin fiber is a general thing, and it's going to be irreducible, so it's going to be stable.
Are you going to say something about the physics part, so the electromagnetic?
Yeah, so maybe I should do that at this point. Do I want to say something else? No, I think that's good. Okay, so let's talk about electromagnetic duality and the classical limit. Let me just say, also, I should say, several other people have said statements like this. Apparently, Housel sent a letter to Hitchin in the late 1990s. And also, Feltings gave a talk in Princeton in 2005, where I had the distinct feeling that you were saying something like that. But anyway, that has been said in various forms. And in particular, this whole electromagnetic duality statement. But I think it's Ron and Tony who really, formulated precisely this conjecture. Okay, so what does this say? So this is the relationship between the Hitchin vibration. So for a group and its Langlands dual. So MH of C, comma G. Let's say complex groups here. You should probably be able to say something about real groups, but we don't have anything to say at this point. Okay, so if you have Langlands dual groups, then the Hitchin vibrations share the same Hitchin base. And furthermore, these are dual abelian vibrations. so this is a statement which was proven in pretty great generality, I think, by Witten and people, and Donagi and Pantev interpret this as saying, sorry? Yeah. Well, I'm not sure whether there's a statement that, I mean, I throw away the discriminant. They probably don't need to throw away the discriminant. I mean, you should be able to probably make a statement that, at least on some reasonable part of the discriminant, should be able to extend, I guess, but I don't know. So Donagi and Pantev interpreted this as giving a classical limit of the geometric Langlands correspondence. But let's look at what this means. This tells us that if we have a point lambda here, so that, remember, lambda is our input to the construction. This is going to go down to a point in Hitchin base. Then if we look at F inverse, so let's call this prim B. Okay, so remember I said that lambda was general, so this is a general point. So this is an abelian variety, some kind of prim variety. And this tells us that lambda is going to correspond to a line bundle L on this thing, okay? And that's exactly what we need to have spectral data, okay? So when I say here that there's a line bundle on Y, okay, so I need to say what Y is here. So Y is going to be a resolution of singularities. So to get Y from the prim, you have to blow some stuff up to make the map well defined. And in general, I'm not sure we know how to do this in general. So we did this. I mean, Donagi-Pantev did this for P1 minus 5 points, and then we did this for a curve of genus 2, okay? In which case it's essentially very much easier than the general case. So this is a problem in general, okay? Well, this is for the group basically sort of SL2, PSL2.
And the same on P1 minus 5.
Yeah. On P1 minus 5 points, it's for SL2, I think. And also balanced weights, balanced parabolic weights.
Do you take the eigenvalues to be 0 in the parabolic picture to get the C star action?
Yes. So in other words, yeah, it's strictly parabolic. Yeah. Yeah, so that's, this presentation, it's a good point. This presentation, of course, is using the C-star action. If you might have a situation which is a Hitchin moduli space, but where you don't actually have a C-star action because the C-star action changes the residual eigenvalues and so on, you'd have to modify the picture at least. I'm not sure what to say in that case. You can probably say something, I guess. But. Okay, so that's what. So I think I've explained pretty much everything that goes in here. So that's how this depends on lambda. The lambda gives you by this electromagnetic duality. This is Kapustin-Witten. Let me apologize if I'm missing any references here, but basically Kapustin-Witten. The lambda is a point of the fiber. Lambda is a point in the LF inverse of B, right? And the duality statement says that this fiber is dual to this fiber, so lambda gives you a line bundle on this fiber. That's supposed to be the spectral data. Right, so yeah, so we're still missing something, but we're getting closer to the problems that need to be solved here. So what we're missing now is that since we blew up stuff here, we have a line bundle here, but we'd like to get a line bundle here, okay? So it needs to be determined what parts of the exceptional divisor, what multiples of the exceptional divisor you put into the line bundle here. That kind of it's very similar to the question about the parabolic structures, because the parabolic structure is going to also occur along these exceptional divisors. Okay, let's see. So I think that's explained. Now what else? What do I want to do next here? Yeah, so I think next I wanted to just sort of say what cases we're in. I've sort of more or less said that already.
So what happened to the line bundle? Where you have this y's that blow up, and where's the line bundle?
Well, okay, that's why I said this, it's a good point. So we had the line bundle L here. We're going to pull this back and get some kind of Ly. As I said, Ly is pretty much well determined by L, except you could add some multiples of the exceptional divisor. So you have to figure out which ones to add, okay? That's the line bundle that goes over here.
Oh, okay.
But as I said, that's sort of a little bit in the wash with the parabolic structure, because we need to figure out what parabolic structure to do anyway. The parabolic structure is sort of like, changing the line bundle by an integer multiple of an exceptional divisor is going to be similar to changing the parabolic structure by some integers or something, roughly speaking. Okay, so when is this known? Let me just, without writing this on the board, parenthetically state that Geitsgori and his whole group of people have now put on their webpage a bunch of preprints that state that they proved the geometric Langlands conjecture pretty much in all generality, I think. But the statement we're making here is, it's about properties of the local system. Okay, so it's true that we would have been happy to do a new case that was not known, but I guess that's not going to happen. But anyway. Okay. The Asteriska of Donagi and Pantev does the case of P1 minus 5 points, where we look at balanced parabolic bundles. In this case, the wobbly locus actually has normal crossings. So that was the question for the next thing. So now we've actually put, if you may, some of you may have noticed, we put the preprint on the web. So then you can go and look at it. So let me quote one of my co-authors as characterizing this as excruciating detail. So in particular, if anybody finds a detail which we're not staying, then let us know and we'll put that in too. Anyway, okay, so we did the case of genus. Maybe I should say here at this P1 minus 5 points and SL2, either SL2 or GL2 bundles. Okay, so for this case, we're really sort of strongly using Donagi-Ramanan description of X, which is a disjoint union of X0 and X1. So X0 okay, so there's the whole theory of the quadratic line complex and the Donagi-Ramanan description of the moduli of bundles. So this is it's not exactly SL2. It's sort of halfway between SL2 and PSL2. So these are degree 0. I mean degree 0 with fixed determinant. And these are degree 1. Determinant. And the Hecke operation goes between the X0 and the X1. There's a C bar here. There's a covering of the curve and so on. So we look at that. And also at the end of this paper, we look at Drinfeld's so in these two things, so the additional question is answered also. Okay. In this here, in the end, we look at Drinfeld's original construction. By Radon transform. For GL2, and show that this satisfies the. But for GL2 and for curve of any genus. And show that it satisfies the conjecture. Show that the spectral variety is as expected. Okay. But we don't do the advanced, this doesn't really talk about the more advanced question. Okay, so let me just give a description of the singularities of the wobbly locus in the genus 2 case. To give some idea as to what's happening here. So also also there's sort of two directions you can go here. The original intention of Donagi and Pantev was to use Mochizuki's construction result to construct the local system. Okay, so the original intention was to define the spectral data, to construct a parabolic structure, to verify that it satisfies the required conditions, which is vanishing C1 and C2. It's kind of automatically semi-stable. It's automatically stable because this Y thing is going to be irreducible. So the spectral variety is irreducible, so it's stable. But the main thing is to get vanishing C2 basically of the parabolic structure. That's the difficult part. there's a different direction you can go, which is what we used here, which is to just say, okay, if we know an actual construction of the Hecke Eigensheaves, then we can just try to apply the theory of direct images for Higgs bundles and you know, see what the Higgs bundle is. And you can do that also. Okay, but let's just sort of look at the singularities of Wob. Okay, so this is sort of fun. Okay, so there's two cases. So there's x0 x0 is P3, which is bundles of trivial determinant, and x1 is contained in P5. So we just fix some point, which let's say we'll take as a Weierstrass point, for example, of the curve. Okay, and now, okay, what does wobbly locus look like? So wob wobbly locus inside x0 is a union of the Kummer surface of degree 4 and the 16 trope planes. This is called Kummer's 16-6 configuration. Now, what do the singularities in codimension X codimension 2 look like? Well, the point is that the trope planes intersect in normal crossings with each other, so that's okay. But the trope planes are bitangent to the Kummer. Okay, so trope it's not bitangent, it's tangent to Kummer. Okay, there's something called a trope conic. I mean, inside these planes, these are P2s. Inside each of these planes, there's going to be a conic, which is the intersection with the Kummer surface. The Kummer has degree 4, but it's the conic counted twice. Okay, so transversely, that's going to be a tachnode. So I should probably say, you might be wondering if you're thinking about this, is this really the wobbly locus the way I defined it? Well, not exactly, because in this case, we're at the moduli space is singular. The moduli space of bundles happens to be smooth, sort of as accidentally speaking, but the moduli space of the Higgs bundles is singular. It's singular along the Kummer surface. And due to that singularity, the Kummer thing actually counts as the wobbly locus also. It's kind of an infinitesimal wobbly locus. Okay. Yeah, so this is a problem, right? So this means, so the problem, why is this a problem? The problem is that we're trying to construct parabolic structures along these things. In fact, in this case, it's not even a parabolic structure. It happens to just be a logarithmic connection that we're going to be constructing. However, it's not a normal crossings point. So in principle, you have to blow up several times and then find a parabolic structure along the exceptional divisors of the blowup. Try to find the best one, so to speak, to make the parabolic Chern class be 0, basically. The parabolic C2 be 0. Now, what about WOB1?
The best one means what?
Well, it's basically the one that gives you the smallest C2, except that has to be Well, it has to be compatible with the Higgs field that you're talking about. So we're given a logarithmic Higgs field here. The logarithmic Higgs field comes basically because of the fact that this y, the map from y to x, this is sort of ramified over the wobbly locus. And the ramification of y mapping to x, that gives you a, if you don't put a parabolic structure on a general point, then that's going to tell you that there's a logarithmic Higgs field. Nilpotent, but logarithmic. And so you need the, this was a subject of much confusion, in fact, but you need the local parabolic structure to be compatible with that Higgs field. And under that compatibility, you want it to have the smallest value of C2. That tells you uniquely what it is, basically. What about WOB1? So WOB1, this is better, it's connected, but so its normalization is just P1 cross C bar. C bar is a 16-sheeted atoll cover of C. But WOB1 has nodes and cusps, and in fact, it has a locus of cusps along there. There's a map from C bar into here. Just take the identity on C bar and then the hyperelliptic map to the P1. There's a locus on which in the codimension x codimension 2 transverse slice, it has a cusp basically. And so again, so in the case of nodes, of course, we know what a parabolic structure is on a node. But in the case of a cusp, we don't really know what a parabolic structure, is on a node. This is where it sort of goes back to Helen's work on Chern classes of connections and stuff like that, which we then worked on with Jaya Ir and then with my student Chadi Thayer. We're not actually explicitly applying those theories, but you could maybe. But if you blow up the cusps, then you're going to get some exceptional divisors, and you'll be wondering what the parabolic structure is. We do this by a trick actually, because the parabolic structure has weight parabolic level 1/2 on the smooth points, so you can actually do a covering trick and get away from that problem. You can actually calculate this without going to the blow up in this case, but in this case we need to go to the blow up. Okay, so that's pretty much one of the problems. So to try to make this program work in the general case, in the direction of using, applying Mochizuki's theorem to construct a local system, one of the main problems I think is you would have to understand what's the singular, what do the singularities of the wobbly locus look like, and what to do about parabolic structures. How to count the C2. If you give a parabolic structure along the smooth points of the divisor, there's going to be a contribution to the C2. And the question is, what is that? So anyway, so I'll stop here.
Thank you. Are there further questions?
Yeah, I have a general question about the Donagi-Pantev conjecture. If you push forward the line bundle on Y to X, and it will correspond to a Higgs bundle.
Yeah.
And by non-Bell-Hodge theory, it will correspond to a local system.
Yeah, that's it.
Should the local system coincide with the?
That's the conjecture. Yeah. But if you put but that's the conjecture is that there exists a good parabolic structure which makes that work. You push forward the line bundle. We push forward the line bundle, but then we get a Higgs bundle on X, but then we might want to modify we might want to put a parabolic structure on that Higgs bundle over the wobbly locus. So that's why it's not easy to figure out what to do basically. And as I said, I'm saying here the problem is to figure out in the calculations how do you actually calculate the condition to make it work is to C1 and C2 vanish. C1 is easy to make, but to get the parabolic C2 to vanish, it's a difficult thing because you have the Wolgamov-Giesecker inequality that says C2 is bigger than or equal to 0. you're trying to get the lowest value.
The prediction is unicity of this parabolic structure, or just a parabolic?
Actually, no, sorry, that's a good point. Thank you. It was another, I mean, it could have gone on more here, but no, we have a case, in the case of x0, actually, with the same wobbly locus, you can put a different parabolic structure. As I was telling somebody, this is my first talk after we've actually done the preprint, but I gave many talks about this before we did the preprint, and including some that were completely wrong, because I was saying, we were the opposite parabolic structure. There's another parabolic structure you can put on here, which has parabolic level 2, basically. And it looks to me, this is a guess, but it looks like that's going to be the thing that's going to correspond to having a lambda, which is a PGL2 local system rather than a GL2 local system of odd degree. And in that case, geometric Langlands tells you should get a local system on x0, but not on x1. So the question, so we have a construction of the local system, but then the question is, you'd like to do it double Hecke, the natural Hecke goes from x0 to x1, but then when you do that, it's not a local system. I mean, it has singularities outside of the wobbly locus. But maybe when you go back to x0 the second time, possibly that becomes a Hecke Eigensheaves for the PGL2 value of lambda, but that's kind of conjectural. But yeah, but just given the spectral data plus the wobbly locus, we have this example where where the parabolic structure is not unique, in fact.
It's not unique.
Not unique, yeah.
And what is the role of genus 2 here? 1, 2?
It's the phrase excruciating detail.
No, because I didn't see it in.
The point is that it's not very easy to figure out what the singularities of the wobbly locus look like in general. But here we have an explicit description.
If you want x0 equal to p3, for example, you better.
Yeah.
No, but yeah.
x0 equals p3. So we can really do the calculations explicitly. So, for example, one question we have, we don't know what's the sort of how bad could the singularities be in general. We've got an example of cusps and we have an example of tack nodes. So.
Is it known whether or not on small pieces of the Betti space that there's like a holomorphic or an algebraic map, or is it not clear? Even in P1 minus 4 points.
Algebraic map from where to where?
The representation of the fundamental group of the curve to the some type of representation of the fundamental group of bun minus warble.
Yeah. So I think that's actually pretty much known because. Now that, geometric Langlands is known for GLN in any case by...
So it's algebraic or holomorphic or neither?
Almost surely yes, algebraic, everything is algebraic. In all the versions, Betti, Dram, and...
So it's not possible to just compute a small jet of it and then it works perfectly everywhere or something?
Yeah, maybe. Maybe that's what... there's these... I'm not sure why, but they love doing an expansion around the opers for some reason, which is maybe what they're doing.
So is the work of Gates-Corey also over the complex numbers?
Well, maybe it depends on which one it is, but...
That's several Gates-Corey.
I find it extremely difficult to understand what actually is happening in the subject.
Sure.
We only managed to understand this add-on transform thing very recently, in fact, but it's been sitting around since 1985 or something like that, or 86. It's actually easy to say what it is. I don't have time now, but it's quite easy to say what it is, in fact. So the geometric Langlands construction for GL2, it's really very easy. You can look in the back of our preprint. It's just a projective duality incidence correspondence using Serre duality. You pull back something and push forward something. So for GLR in general, for general rank, it's a more complicated thing because in Le Mans Bourbaki seminar, there's a whole sequence of blow-ups and blow-downs, in which case you do Fourier transform. So that looks like it might not be algebraic because it's Fourier transform. However, apparently Fourier transform in the conical case is actually preserves tameness, so to speak. So you should be able to write down explicitly. Yeah.
Is there any kind of like hidden motivation that in the original case it's like counting points on spaces, and that's related to modular properties? Is there some possible enriched version which has some type of interesting functions or expansions or something?
Oh, maybe there's people doing a seminar. There's people doing a seminar about that. I don't know if Maxime's probably not here, but yeah. There's people who do things about expansions of geometric Langlands things and stuff like that. Actually, reading Drinfeld's paper, I sort of got the feeling that actually this Higgs picture maybe could be considered as very similar to this counting points picture, because the counting points picture, you have these Frobenius elements, so you're basically looking at the eigenvalues of Frobenius. And here you have the Higgs field, and we're basically looking at the eigenvalues of the Higgs field. So maybe in some vague way, maybe the spectral curve, maybe the spectral variety of this thing is sort of like the eigenvalues of the Frobenius, possibly. But I mean, I wouldn't speculate too much on that myself. But
is that the comment you wanted to make in characteristic P or unequal characteristic?
No, sorry. The comment I wanted to make in characteristic P is that, okay, so I'm not sure how apparent this is, but we're working on here we're really working with a point in the Hitchin base, which is general. Okay, so because we want the fiber to be an abelian variety, so we can make this electromagnetic duality thing work. Okay, and all the characteristic P and P-etic, non-abelian Hodge theory stuff. It seems to me tends mostly to have some kind of no-potency hypothesis in it. Something or other, the Higgs field tends to be supposed to be no-potent in some way, or the connection or something. I mean, so anyway, again, I'm totally not an expert on this at all, but what I was thinking is maybe you could say in the Hitchin base, you could say, okay, let's look at the no-potent cone in the Hitchin base, then do sort of a formal neighborhood of the 0 point in the Hitchin base. Then you could have sort of a rigid variety where you might have a sort of a rigid thing which was actually an abelian variety in the rigid sense, which would be the fiber, sort of the generic fiber, but really near to the no-potent cone. So that was what I wanted to say. But again, that's a total non-expert comment.
So if you have lambda which is not generic, like maybe it carries a CVHS or something, can you access the corresponding Hecke Eigensheaves by taking a limit?
You mean you approach lambda by a limit and then take this thing and see what limit it is? Oh, that's a good question. We didn't think about that. I mean, probably. Given Field's question, which is, is this correspondence algebraic? And it should be, I mean, given the fact that it's given by some kind of push back and pull back and push forward operation in general, which is going to be algebraic mostly. I mean, that type of thing could be algebraic, but maybe it's not it could be constructively defined or something like that. So maybe you have to be a little careful. But I mean, I think that's a reasonable thing to ask for, yeah.
All right, so if there are no other questions, let's thank Carlos again.
Okay, thank you.